My name is Rob Farber. I'll be talking about the impact AI is having on the HPC community. In a word, the impact is everywhere, from hardware design to algorithms and even the techniques and approaches scientists are using to address problems in HPC. I apologize in advance for the choppiness of this presentation. Due to the pandemic, I can't be there in person. I use Microsoft PowerPoint to create this video. PowerPoint has problems when recording audio on slides with animation. As you will see, I make heavy use of animations to convey the dynamics of the material. Before starting this talk, I'd like to personally say, please stay safe, wear masks, and practice social distancing. Besides, we all get to look like bandits. While I love the massively parallel computing capability of GPUs, I also note that modern CPUs are now also good for AI applications. This includes training of the neural networks. It's all about the memory bandwidth. If you don't have enough memory bandwidth to keep the computational units busy, it doesn't matter if you're running on a CPU or a GPU, you're just not going to get the performance. Happily, CPU vendors have gotten the message. For example, Intel now offers chipsets, specifically the Intel Xeon Scalable 9200 series, that has 12 memory channels going into each chip. And each chip has 2 AVX512 vector units per core, so you can get high floating point performance. Similarly, AMD does really well with 8 memory channels per chip. And what they do is they boost the clock rate of the memory to feed their AVX256 vector units. I do make the overall observation that GPUs are also getting too wide for many workloads. When I'm working with students in a lab and they're doing training operations, I see that they're getting very low GPU utilization just because they don't have enough training examples to keep the GPU fully fed. I also point out that the NVIDIA Ampere A100 design is partitionable now. While this is slated for a cloud environment, I also think it's recognition that GPUs are getting too wide for many computational problems. I also make the general observation that high-end AI-oriented CPU and GPU costs are getting really pricey. Essentially, vendors are now selling platforms. This is analogous to the luxury car market, where dealers want you to buy platforms with all the bells and whistles. The challenge for us is where do we fit these platforms into an HPC cluster environment? So our observations so far is what we see is MIMD, which is what CPUs use, multiple instruction, multiple data. It's messy. You have to program it correctly because there's locks and critical sections which can serialize your code. However, MIMD architectures are good for all HPC applications. ANNs use SIMD, single instruction, multiple data. SIMD is a subset of MIMD, and in general, it eliminates the needs for locks, mainly. You can do data parallel operations, and of course, there's atomic operations for reductions and other critical operations like that. So it's good for many, but not all important HPC applications. That's why you have to consider your workload mix. I also point out that data scientists use frameworks such as TensorFlow, PyTorch, Caffe, a number of different ones. And these provide essentially a high-level transparent interface. As long as you load the appropriately optimized application for CPU or GPU, they're going to get good performance out of that particular hardware platform, at least up to the capabilities of the platform. So you don't have to worry about having the data scientists reprogram for each of the different architectures. The key question then becomes, what is your workload mix? This slide conveys a key concept I'd like you to take away from my talk, that you don't have to have a GPU to perform AI. So there's two kinds of operations in AI. The first is inference operations, and this breaks down into either latency optimized inference, which is typical of most HPC workloads. Essentially, you take a data item, pass it through the neural network, the trained neural network, get the result, do something with it, and move on. There's low or no data parallelism. The second is batched optimized inference, which is typical more of a commercial environment where you have many users making requests, and all those requests can be batched up, and you generate the outputs all at the same time and then send them back to all the various users. So as far as latency optimized inference, there's 3 kinds of devices that perform well. In other words, they have very low latency. The first are ASICs, which are not a factor generally in HPC because they're custom devices and not really configurable. FPGAs are reconfigurable devices. They're actually very interesting. They're hard to program, but they're getting better. And then the third is CPUs, which are able to perform essentially these sequential inference operations well because they don't have to call an external device. Instead, the thread of execution runs on the CPU core, and if you can exploit both data locality and the internal ANN parallelism to get vector capability out of that as well, so much the better, and you get really good performance. Conversely, batch optimized performance aggregates a bunch of data items and you run in a thread parallel fashion. And it turns out that a recent benchmark comparison between an Intel Xeon Platinum 9282 that it beat an NVIDIA V100 and an NVIDIA T4 inference optimized GPU on batch parallelism in the ResNet 50 benchmark. This is not to debate the validity or the efficacy of that particular benchmark result, but rather just to point out that CPUs are competing with high-end GPUs now. I'll also point out, as will be discussed later in this talk, that training is a batch inference operation. Basically, you're doing a batch inference over the training set and repeating that according to some numerical algorithm to find a minimum error. Overall, you need to consider your entire workload mix, and HPC workloads span a variety of different applications, many of which are not SIMD friendly. So you need to consider, is a GPU enough, or do you need a high-end CPU that can do everything fairly well? Let's take a look at the field of AI and why this machine learning technology is so powerful. Back in 1957, there was the development of something called a perceptron, which looks very similar to today's neural networks, where it adjusted a series of weights and used linear combinations of these weights to solve problems. Well, in 1969, Minsky and Papert basically killed the entire field of machine learning because they observed that they could only solve linear problems. The perceptrons could only solve linear problems. And the world is generally nonlinear, so even something as simple as an exclusive OR problem, XOR problem, could not be solved by perceptrons. Well, in the 80s, there was the development of backpropagation and the use of nonlinear neural networks, where they used a sigmoidal transfer function to learn how to solve nonlinear problems like XOR from data. And that created a huge bandwagon effect. Let's take a look at why this was such an important advance, because these technologies still make a big difference in today's data centers. The importance of nonlinear artificial neural networks to solve the XOR problem cannot be overemphasized, and it explains in significant part why AI and machine learning is so prevalent in today's data centers. Basically, with the ability to wire up to solve the nonlinear XOR problem, a neural network can, in theory, learn to solve any computable problem from data. The argument is very simply that if the neural network needs to, it can wire itself up into any of the logical components of a digital computer. A digital computer has been proven to be computationally universal, so in theory, the artificial neural network can solve any computable problem, just like our brains, for example, can solve any computable problem in theory. To demonstrate this, Terry Sinowski came up with a beautiful example of solving a very complex nonlinear problem, how to read aloud by showing it a segment of text and the phonemes that should be pronounced in the data set. And he also used this as an example of how to do a beautiful bit of scientific showmanship. Essentially, Terry showed up with a tape recorder showing the neural network halfway through its learning process and the sounds that it would make. Well, Terry also learned that psychologically he had to use a child's voice because it unnerved his audience if he used an adult voice. What really drove the point home is hearing the network after it found a local minimum.
I like to go to my grandmother's house. Well, because she gave us candy.
The key point is that with that low error, the network was able to pronounce the words in the training set correctly. More than that is that it had generalized the solution because it could pronounce words that were not in the training set. Well, We could extend that to other languages, other English language, other human languages, excuse me, and also the language of DNA, as shown by the paper by Alan Lapides and myself, showing how to predict coding regions in eukaryotic DNA. The following shows the data parallel mapping I created during the 1980s for training neural networks in a massively parallel fashion. This mapping runs with high performance on both SIMD and MIMD devices and exhibits near linear scalability. It is literally exascale capable and allows us to train with as much data as we wish and, subject to device and network limitations, as fast as we wish. Training a neural network starts with selecting a numerical optimization algorithm, a black box. That black box optimizes an objective function. I highly recommended using the LBFGS method because I find it delivers time to model on the orders of seconds for complex problems where conjugate gradient and other methods take hours or days for those same training sets. Basically, LBFGS uses both the Jacobian and the Hessian matrices, and if you need to, use VLBFGS if you have billions of network parameters. This mapping starts by broadcasting the black box network parameters, or model parameters, over to all the devices in the network. This takes constant time, meaning it takes the same amount of time to broadcast to one device as every device in the system. After that, each device calculates the partial errors of the model based on the model parameters for those training examples that have been preloaded into its memory. There are no dependencies between devices, so scaling is linear according to the number of examples in the device memory. It scales perfectly in a distributed environment. Finally, a reduction operator is used to get the error over the entire training set. This typically runs in log time on most network architectures. Hence, we see an overall near linear scaling for the training run when running in a distributed cluster environment. As can be seen in the far right, this mapping works nicely with external devices like GPUs. In fact, as you can see, we have a path to exascale with those straight lines going along, and we can just keep adding computational units, whatever it be, CPUs, GPUs, FPGAs, in order to train on as large a data sets as we need, and with certain caveats, as fast as we want to train, at least as far as the computational iteration, not necessarily in terms of the number of iterations needed to achieve a global minimum. And I always stress report honest flops. That data parallel mapping that I showed you effectively solves the problem, at least the computational problem, of getting the error, calculating the error, regardless of the computational hardware platform that underlies the supercomputer, be it a CPU or a GPU. And we get that beautiful near linear scaling. So that, of course, does not address the issue of what's the best numerical algorithm to avoid false minima and getting trapped in local minima, but that's a topic that is beyond the scope of this talk, and it's a very interesting research project in and of itself. Instead, let's start taking a look at the applications which has made AI so powerful and so prevalent in our modern data centers. And I will essentially follow the form of Terry Sinowski's Net Talk, where we see that you've got a 5-letter window with the phoneme pronounced at provided as the output in the training set from the center letter, the X in this case, in that example that you see up on the screen. So I also mentioned that Alan Lapides and I used this same type of a technique to learn coding regions in DNA. So we gave it the base pairs and what is the coding identification, coding or non-coding, for the central, in this case, the G in the data set, in the center of the window. So we use the same trick. And I'm just going to keep that same form to keep everything relatively simple for people here, not because you can't get it, but just because I have a limited time to convey a lot of information. So I'd like to tell you about the computational drug discovery company that I formed and how we use this technology for small molecule drug designs. I can only talk about the public part of the data, but I think you get the point, and it will also show how you can do wonderful things with neural networks. So if you look at binding affinity, which is how drugs work in the human body and in nature, we use an example, an antibody-antigen binding complex. And yeah, there's this Y-shaped thing, and there's some kind of a target antigen that it has to glom onto, and it doesn't look too bad, right? Well, as you start looking at the biology, it becomes a lot more complicated. And actually, the deeper you delve down into the problem, it becomes more and more complicated, and it gets uglier and uglier. And then actually, if you go to first source data like the electron microscope, boy, does it look ugly. So it's a complicated problem indeed. Well, Alan Lapidus and I and a group of other people basically came up with a way to solve this problem, and we presented it to a major pharma. And the research executive committees went away and they came back with an excellent question, which any of you who work in machine learning should ask of every project. And that question is how do we know that you're not playing expensive computer games with our money? Well, the way that we addressed it is we suggested a double-blind experiment. Remember that the neural network is just performing an optimization during training to adjust a bunch of parameters to fit a surface. So that may or may not have any reflection in reality of what's going on in the real world. Our assumptions about what is correct and physical do not apply in this environment. The neural network could be doing something completely off in la la land and predicting something we don't want. For example, a classic example that I use is a national lab took a bunch of pictures of tanks and cars, and they wanted to have a neural network identify the difference between the tanks and the cars. The training set did beautifully, the cross-validation set did beautifully, but when they took it out in the field and tested, it turns out that performance was abysmal. Actually, it was probably worse than random chance, but not enough to be useful. The funding agency said we spent a lot of money on this, figure out what happened. They did, and they found out that most of the pictures were taken of the tanks on a cloudy day, and most of the pictures of the cars were taken on a clear day. So the network was just learning the difference between a cloudy and a sunny day. That's the same idea that we have to apply with our skepticism to see, are we actually doing something that solves a real problem? In this case, again, I use the format that Terry Sinowski used, in that we present a 5 amino acid hexamer to the network for training, and for the examples, we have a known binding affinity for a specific antibody. Well, there's 20 to the 6 possibilities, or 64 million options that we can cover. So we went to our favorite chemists and they said, can you give us data? And they said, yes, we can. But we were doing drug trials, and so we were focused on specific types of hexamer antigen antibinding complexes. So there's going to be a lot of data in a few spots on that multidimensional surface and not many on a huge amount of the surface. In fact, we had data approximating 0.001% of the data, which actually was great because you're never going to have enough data to encompass all of chemical space. So it gave us an idea of the generality of the system. Such small amounts of data are not unusual in real problems where people have to pay money to actually gather data. It's not like having an internet stream that's a data set that's collected fairly cheaply and easily. And so what we did is we took a few thousand hexamer examples and we trained up our network. Again, this would not have mapped well onto a GPU, but would have worked on a CPU. And so that's something to keep in mind, is that real world problems don't necessarily always mean that you have huge amounts of data. At the end of the day, after training, we were lucky and we actually trained up and found a set of parameters that gave us a very low error in terms of predicting the binding affinity based on our representation of a hexamer of the different amino acids. So what we did then is we used this in a hill climbing method because we actually had a mathematical function that we could apply and do some sort of an optimization on that in and of itself. So here's a representative surface, not applicable to the drug discovery, but just one where we can see the hill climbing method in operation. And it was a very simple method. We basically took a default, everything the same hexamer amino acid string, and then we iterated through all the possibilities in one position, and we kept the highest value. And we did that then for each position, ran through all 6 positions, and at the end of the day, we made our prediction. We found a particular hexamer that we predicted would be 6 orders of magnitude higher, approximately, in binding affinity than any of the data we had actually seen. So we took that, wrote it up, and said this is where we're putting our money where our mouth is, or our request for funding, where our prediction is. And we went to our favorite experimentalists. They actually made that hexamer, performed the binding affinity experiment, and came back and said, yes, it is very high, and in fact, it is approximately 6 orders of magnitude higher than any of the data that we gave you. So your findings appear to be valid, and we like this idea as far as a computational approach. That tied the link between what's happening in the real world to the computational model. And again, this was done with 1980s, 1990s technology, and makes the point that you don't have to, and you generally don't have, a huge amount of data for real problems where people have to spend money to gather the data. Another quite valuable application of neural networks is essentially creating a nonlinear crystal ball, creating a nonlinear system model for prediction of system behavior. And again, using the format that I've been showing based on Terry Sinowski's net talk, basically we're able to take a series of constant delta samples at time t, t minus 1, t minus 2, and so on, and predict a time t plus 1 in the future. We then train up our neural network to predict t plus 1, and again, that gives us a function, which we're then able to use by iterating, where we can actually make that prediction in the future. And then we essentially slide the window down. So we take our prediction, feed it back into the model that's been learned by the neural network, and we're able to iterate some number of steps, in fact, an arbitrary number of steps in the future, and look at how the error shows deviation from the real data. So we examined several different types of non-trivial systems, the logistic map, the Mackey-Glass equations. And in predicting the future, we actually then provided a root mean square error plot of our method in the black line compared to other techniques, the best known techniques as of that time for, again, non-trivial complexity time series. And we see that the root mean square error actually does very nicely and performs, you have much less error as you iterate forward in time compared to the best known methods as of that time. That's again in that How Neural Networks Work paper. I don't mean to give the impression that all of the work that was done during that time frame was based on this simple framework by Terry Sinowski. So I highlight a bit of work performed by my friend Yanis Krevakridis that I was able to participate in. Basically, Yanis recommended that we embed a neural network in an integrator, in this case an RK4 network. We present it with the dynamical time series data and train the neural network up to be the quote-unquote system of equations for that reflects that data. It's a true system model. The example we gave in 1993 was for a van der Pol oscillator, but it's applicable to a larger number of dynamical systems. It's a beautiful bit of work because you can then perform the bifurcation analysis on those systems of equations. We've applied it to electrical systems, data flows. It's very good for stiff sets of equations for those of you who are mathematically inclined. For those of you who are not, I'll give a mechanical example, is if you've got a rotating turbine and it gets hit somehow and it starts vibrating differently, that's a bifurcation, and you can actually predict fairly accurately the bifurcations. I will also put in a plug for my friend Yanis, is that if you are looking to get a PhD, you could not do better than having Yanis, who's now at Johns Hopkins, be your advisor and your teacher and mentor. He's a wonderful guy and a stellar researcher. As my final example, I showed that neural networks can deal with high-dimensional data. Said succinctly, they can deal with the curse of dimensionality. when you have high-dimensional data points, or points that reside in a high-dimensional space, when you want to search to find other data points that are similar to one of interest to you, the search volume increases so rapidly, essentially exponentially as the dimensionality increases, that that sphere or hypersphere that you're using to search finds too many data points. In other words, you can actually have literally the entire data set returned, because in really high dimensional data, in some sense, every data point is a nearest neighbor to every other data point. Or the search volume that you're looking for doesn't return any results at all. There's nobody who's really considered as a nearest neighbor just because the volume's too small. Similarly, we can also use dimensionality reduction to actually help us visualize data, because people do well only in visualizing three-dimensional data. Yes, we can add color to maybe get 4 dimensions, but for example, if we have 100 or 1,000 dimensional sensor data, there's no way that we're going to be able to visualize that as a surface. What we can do though is we can take a big data set of that high dimensional sensor data and pass it through essentially a neural network that has a series of bottleneck neurons. In this example, we take the input vector, pass it through a set of 3 bottleneck neurons. That will give us an XYZ set of coordinates that we can visualize. The upper part of the network, not shown, actually reconstructs from that low dimensional representation, a compressed representation if you will. It reconstructs the input vector at the outputs, and that's how we calculate the error to see how far off the parameterized model gets us to our ideal of a perfectly reproducing set of bottleneck neurons. Then during the inference operation, what we can do is we can take that high dimensional data, generate our 3-dimensional XYZ coordinates, and assuming if we have low error, we actually have a good 3-dimensional manifold that we can visualize and deal with and operate with as people. And the sense of who's near who also makes sense. Euclidean distance makes sense. If we have a purely linear network, then we have a principal components analysis. If we have nonlinear computational units in there, then we have a nonlinear principal components analysis. Both are very powerful data analytic tools. With all these capabilities, it's proof on how overblown the promises made by the putative experts were in the field, because we essentially had this desert wasteland occur again, even though there's these tremendous capabilities. Not surprisingly, when researchers again mimicked the capabilities of Mother Nature, essentially with the introduction of deep learning and the introduction of convolutional computation units into neural networks, mimicking the behavior of the mammalian visual cortex, we found that machine learning and AI found a commercial niche, because you could actually start doing wonderful things with images, and the field basically took off because there was a strong commercial need for this type of technology with the internet, but also NVIDIA provided a massively parallel computing architecture that supported very fast training, and it just completely reopened the field into the current modern day age again of another bandwagon. Lesson learned here is twofold. One is every time we mimic what Mother Nature does, we get big improvements we tend to get big improvements in machine learning AI capability. And secondly is be careful of the bandwagon effect and overpromising what the technology can do. As we enter the exascale era, people are rediscovering machine learning and all their capabilities for time series analysis, bifurcation analysis, everything through to expectation maximization and independent component analysis. We have the computational framework, we have mature software frameworks, so it's not surprising that there's wide adoption of this technology. This is not an AI history talk. So deep learning is a commercially viable technology encompassing much of what we do. DNN for speech, so you can do speech to text recognition, better than human face recognition, self-driving cars, robotics, self-guiding drones, and much, much more. There's a huge commercial viability to this technology. So everything we've discussed and more, all with newer computational platforms being supplied by all the vendors to meet the need for this technology. I'd like to highlight now a milestone achievement at CERN that shows the ability of machine learning to impact physics-based simulations. In the past, when I've tried to incorporate machine learning into modeling and simulation, the traditional cornerstones of HPC computing, the question came in as, well, this is a data-derived model, and can you tell me what that model is doing? No, I actually can't. Then the next follow-on question was, well, how do we know that your data-derived model is not going to introduce some non-physical artifact into my physics-based simulation? And I could not guarantee that. The CERN research actually changed all that, because what they effectively did is use something called a generative adversarial network. And essentially they train up a neural network to generate a probability distribution based on the data that it sees, and an adversarial network which tries to identify if it's a fake or a real piece of data. And as the system learns and gets to lower and lower error, it converges to the point where the adversary becomes so good that it creates the generator, creates a generator that is actually so good that, as Sofia Valle-Cortez points out, the generator is so good that it's indistinguishable from the real data distributions. And once you've achieved that point, then there's no reason not to use the data-derived model, because you can't distinguish the distribution of events that it produces from the real data. The nice point is that this is literally orders of magnitude, many orders of magnitude faster. For example, the computational model to run the full Monte Carlo takes 17,000 microseconds, whereas on a GTX 1080, you can actually do that same generation in 0.04 microseconds. So it's very, very fast. It's enabling a new era in physics research, because researchers can now investigate what happens when they move the collider up to higher luminosity. But more than that is, we're seeing this approach moving into other traditional mod sim HPC simulation models. Deep learning has also made an impact on the scientific community. For example, in climate modeling, it's possible to run a climate simulation and come up with years and decades worth of climate data. That's just too much for a human to look over. So instead, what scientists do is they use a visual-based neural network to categorize storms by type. In this way, they can actually have the neural network run through the simulation data, identify the storm types, create a probability distribution of the storm types, which, say for example, if they're comparing against historical data, they can see if the model reflects what the historical record shows, and if so, then they validated their climate model. At this point, I hope I've sparked your interest in the power and capabilities of AI and how it's impacting the HPC communities and how science is actually being done. As far as today, the debate is between general purpose devices like CPUs and GPUs for training and also for HPC simulation. In the near term, I see that data flow architectures are going to become more prevalent, and FPGAs are a likely candidate because they're programmable in the field. ASICs are also a possibility. Neuromorphic computing, I project, will redefine what is possible with AI. So there's basically 4 different vendor camps, and I've incorporated the logos in those different areas for basically chips, CPUs, and GPUs. As far as in the far term, quantum compute is a big compute, small data problem. And I just like to use the expression Thomas Sterling uses in describing quantum computing, that is Computer Science 101 at Hogwarts School of Magic. Mother Nature does not require that biological brains have high numerical precision. Computer scientists and vendors have capitalized on this fact to implement reduced precision hardware accelerated math operators, which can be used to perform inference operations with high accuracy. This is wonderful, and further, HPC scientists are now investigating the potential of these reduced precision operations to speed numerical simulations. Much of this work has been focused on the BLAS libraries, which are a cornerstone of HPC computing. I refer people to the Ideas webinar and the HPCG, HPL, Magma, and Plasma projects to see the impact of these reduced precision math libraries and the speedups that are possible. I also like to point people to libxSMM. Many HPC applications rely on batched small matrix operations. Well, libxSMM provides a BLAS interface to do this, but further you can use reduced precision operators to perform calculations. It's a good investigatory tool. I also like to highlight that because scientists are examining precision and how many bits of numerical precision do we actually really need, there's the HICMA library out of KAUST, which gives scientists the ability to perform million by million matrix operations while only requiring gigabytes of memory. Think about it. A terabyte matrix that can be solved or operated on in a gigabyte memory space workstation. DAGs, direct acyclic graphs, are also changing HPC because basically you want to exploit all the parallelism inside the neural network as well. And that means that you first map the computation of the neural network to a DAG, and then basically, depending on the dependencies of the calculation, try and incur as much data parallelism as you can, or parallelism of the computation as you can inside the graph, while also localizing, making the best use of locality of parameters in that to reduce data movement. So we're starting to see some really nice incorporation of advanced computer science techniques into HPC tools and algorithms. Further, the HPC Center is changing completely. I highly recommend looking at the BDEC, the Big Data and Extreme Scale Computing Project, where actually the HPC Center and Cloud, it's no longer a pinnacle of computation. Instead, it's part of a distributed set of services that extend all the way out to the edge where your sensor data is. Think dimension reduction, for example, and the usefulness of that in examining your data. So I highly recommend looking at the BDEC report. Frontiera, which is the new and largest academic supercomputer at the Texas Advanced Computing Center, is an agile HPC system. I'm very impressed with how the TAC team is incorporating cloud into their HPC framework. And as they note, this lets users investigate new technologies because cloud centers, data centers, are usually deploying the latest, greatest hardware so that people can start using that. This is a way for HPC centers to start investigating the efficacy of new data and to start using that. Argonne has a huge database data service based on Petrel, and that means what that means is that people are looking at the problem of when your data sets become so large that it's impractical to start moving them around, so you want to start analyzing them in place. It's a brave new world. There's a lot of new technologies and capabilities being introduced. It's an exciting time in AI. The success that AI technology has enjoyed commercially, causing a widespread application of the technology because there's a profit motive, and the impact that it's had on system vendors has been extreme and profound. It's not bad for surface fitting, but we have to take a look at what's next. To do that, we have to understand how the technology is working at the moment. And basically with that surface fitting, when we're doing our interpolation, our inference operation, we're interpolating on that surface, sometimes between the data points that were provided in the original training set, and that tends to be a more accurate form of predictive capability. Or we're extrapolating out from points on the surface, which is less accurate because you're more dictated by the whims of the numerical optimization algorithm. Speech to text is one classic example where people have problems with this, where we experience it in our real-time daily lives. And for example, I received a birthday card in the mail which said herpes bathtub, which is an unappealing concept, I think, to everyone. When you open it up, it says happy birthday, damn voice recognition. That basically summarizes it, I think. There are limits to the current technology. It doesn't deal well with noise, and it doesn't have really a concept of context of the words. Further, given we have so much computing capability to use for training our neural networks, we can utilize ever larger data sets to train on ever more bumpy surfaces, meaning more complicated problems. Here's a nice graph I received from a friend at Intel showing that people in the upper right-hand corner are actually training with neural networks that are huge, literally with billions of parameters. This means that not only is memory bandwidth important, but memory bandwidth capacity is becoming an issue. Further, there are becoming more and more problems with actually generating a clean data training set for those large training runs. This has caused new technologies to be developed, and it's very exciting. The first is the Intel PMMs, which are persistent memory modules. And this allows essentially the creation of very fast fat nodes that have terabytes of main memory at a fairly cost-effective price point. Lenovo has done some research and evaluation of this technology, and they note that on a single workstation they can get multiple tens of gigabytes per second of throughput and literally access data in nanosecond latencies. This gives the ability to train with ever larger parameters and also to process big data sets more in memory than externally. Further, we were actually seeing a breakout of the POSIX stronghold on storage. POSIX is wonderful, but it does have some serial bottlenecks that were designed into it. For example, the A time is actually the access time is one example of that. So the HPC community has gotten together and created a new file system abstraction called DAGs, and it's really quite wonderful. You essentially can access persistent storage from user space. This bypasses all of the bottlenecks that exist in the POSIX abstraction, because you don't have a system call to access external data, you don't have to go through a page in a block cache, there's no PCIe overhead, and you can literally get your data in a few tens of nanoseconds from storage. Aurora will be the first production deployment of DAGs on the Exastel system, and that's coming in 2021. As far as the next step, we're seeing hardware implementations of neuromorphic computing devices. Basically, neuromorphic computing is based on a spiking neuronal approach, which is basically how our brains work, how all mammalian brains work. And as a thesis that I've been presenting in this talk, every time we mimic what Mother Nature does, we tend to get improvements in our predictive capability and also in our functional capability. So I referenced this Proceedings of National Academy Science paper done by IBM, which showed that neuromorphic computing can actually approach and match the state-of-the-art classification accuracy on neuromorphic computing hardware as the best state-of-the-art current digital ANN based models. Further is neuromorphic computing devices use orders of magnitude less power. So our brains, when they're operating, burn about 10 watts of power or so. Neuromorphic computing devices operate in the milliwatt range, which means that you can get extraordinary capability even in IoT devices where it's possible to run a neuromorphic inference engine using just the heat difference between your wrist and the outside air temperature. It's a very exciting development. There's hardware efforts by a number of different vendors, so this is something to keep an eye on. Here's an example from IBM where they've built a system roughly of the neuronal size of a rat brain on a desktop. So we are seeing the advent of the future, and again, as I point out, this is technology to watch. Thank you for your attention. If there's time, I'll be happy to answer any questions. Otherwise, please feel free to contact me at the email address in this slide.